Okay, so welcome to this live session on week 11. Okay, so week 11 basically it is about state space approach. So state space analysis. Okay, so then pole placement to design, then observer design, then Kalman filter. Okay, so now week 10. So week 10 and basically week 11. Okay, so they are combinedly discussing the week 10 basically introduces the concepts of state space analysis. Okay, so the week 10, if you see, okay, so what do we have? So you might have seen the so definition of what are the states. Okay, so definition of state x of t. Okay, then given the system, okay, if any system is given, okay, let us say any mechanical system or electrical system. Okay, so first what we do the modeling. Okay, so we do the modeling in this sense, we use the physics laws, so using kinematics, dynamics if it is a mechanical system, or if it is electrical system, we basically use KVL, KCL, and we write the differential equations. Correct? We write the differential equations. So in the state space approach, basically what we do using these differential equations, so we form something called as the state space equations. So state space equations. Okay, basically those equations are uh, in the basically we get these equations. So something like x dot is equal to ax plus bu. Okay, and y is equal to cx plus du. Am I correct?
Yes, sir.
Yeah. So these are called as the state space equations. Okay, first equation we called state equation. Second equation is called as the output equation. Okay, so state equation as well as output equation. Okay, so that is one concept you might have learned. And in the week 10 itself, you also have seen the linearization. Okay, so linearization means once we write these differential equations, sometimes what you will get your equation is x dot is equal to f of x. Okay, so here f of x could be a non-linear function. Non-linear function. So in that case, we perform something called as the linearization. Okay, so that will convert our system to this model x dot is equal to ax plus bu, which is a linear system. So x dot is equal to ax plus bu is a linear system. Okay, it means that linearization basically what it does is, so we get these differential equations in this form which are non-linear. So using linearization, we convert them into, so x dot is equal to ax plus bu, which is the linear form of the equation. Okay, so basically state space equations in this course, what we deal is the linear state space equations. Okay, that is one thing. Then we also have seen the state transition matrix. Okay, state so transition matrix. So you might have seen something like pi of t, which is equivalent to L inverse of Si minus A whole inverse. Okay. Then you might have seen the transfer function also. Am I correct?
Yes, sir.
Yeah. So these are the topics at the outset covered in week 10. Okay. So basically now week 11, we will continue the same thing. Okay. So in continuation of all these concepts. Okay. So specifically, we design something called as the two concepts which are called as the controllability and observability. Controllability and observability, continuing these concepts only. Okay, next to these concepts. Then, based upon controllability, we discuss this method, pole placement. Based on observability, we discuss observer design. Okay. Then, as an extra topic, we'll be discussing the Kalman filtering. Okay. So now what we do is in this slide. Okay. So we will cover these two things. Okay. So controllability, observability, and pole placement design. Next slide, we will see this observer design and Kalman filter. Okay. Hope this is clear. Okay. So let me share my screen. Yeah. Okay. So these are week 10 concepts. Okay. So state space representation, linearization, state transition matrix, and transfer function. Okay. The transfer function is already covered there, but here we'll see it again. So the first equation is called as the state equation. The second equation is called as the output equation. Here output, instead of Y, we are representing that with C. Okay. These matrices are A, B, D, E. So instead of C and D. So those are also fine. Okay. So now if you take initial conditions 0 and apply the, because basically first equation is the differential equation. Okay. If you apply the Laplace transform to the first equation from here, take initial conditions 0. So you get this one. Then Laplace transform to the second equation. Okay. C of S is equal to dx of S plus E R of S. Okay. So from these, do the little adjustments in the equations. And finally, what is your input here? Input is R of T, output is C of T. Basically, what is transfer function? Output by input. It means that C of S by R of S. So adjust these equations, remove this X of S, okay, and find the expression for C of S by R of S. Okay, if you do that, so this is G of S, which is nothing but C of S by R of S. You get this expression. Okay, this is the expression for the transfer function. Okay, so is there any doubt here in this? You just need to modify the equations. So find this expression C of S by R of S. Any queries here? You can check this derivation. It has been already explained in the video also. Okay. Now, if you see this, this is our first expression. Okay, transfer function. Okay, so transfer function. Okay, so which is nothing but C of S by R of S. Now, here this part is the inverse of a matrix. So basically, how do we define the inverse of a matrix? Adjoint by det. Correct? Adjoint by det. Okay. So you can see that in the denominator we have det, Si minus A. Okay. So now in the transfer function, basically what is the definition of the poles? Okay. So poles definition is that you have to make denominator to 0 and find what are the roots. Am I correct? Am I correct? So we are making this denominator to 0. Okay. So this is our definition of finding the poles. Am I correct?
Yes, sir.
Yeah. And in the matrix theory, we know that. So basically what this equation gives us, this equation will gives us, okay. So if you remember the matrix theory, instead of S, if you have lambda I minus A equal to 0. Okay. What this one gives? This one basically gives the eigenvalues. Am I correct?
Yes, sir.
Yeah. So it means that here we are getting poles. Same equation in the matrix theory, we are getting eigenvalues. It means that the poles are nothing but the eigenvalues of matrix A. That is our conclusion. Okay. It means that if x dot is equal to ax plus bu given to us, okay, what are the poles? The poles are simply nothing but the eigenvalues of matrix A. Those are nothing but the poles. Okay. So once you know the poles, so we can decide the stability of the system, okay, by plotting the poles on the S plane. Okay, if all the poles are located on the left hand side of the S plane of the omega axis, we say system is stable, otherwise unstable. Okay, so here poles are nothing but the eigenvalues. Simply how the eigenvalues will look like. Okay, that will decide the stability of the system. Is this clear?
Yes, sir.
Yes. So that is our first step comes from the transfer function. Okay. Now, so the major topic is controllability and observability. So basically, these are the two concepts for any system. Okay. So which they will help us to talk about the uh, best solution in the system. Okay. So you don't need to understand what is this optimal control problem. So basically, this controllability will basically, okay, it is related to the, okay, uh, related to, can we control the system? Okay, if it is unstable, can we make it to stable? Okay, how can we say system is unstable when some poles are existing in the right hand side? Okay, how can you make system stable by pushing the poles to the left hand side? Am I correct?
Yes, sir.
Yes. So controllability basically talks about how to push those poles from left hand side, right hand side to the left hand side, or from uh, if all poles are say, existing in the left hand side, but if they are very close to the j omega axis, how to push them more away from the j omega axis. Okay, so the controllability talks about if you have poles here. Okay, it talks about how can we push these poles this direction or any desired location which wherever you want. Okay, that is about controllability. Okay, whereas observability, okay, observability basically talks about, okay, so to do this controllability or to move the poles more from the existing poles, okay, you need measurements of the states. You need measurements of the states. So the observability talks about the measurements of those states. Okay, can we measure or not? Okay, so the controllability assumes that all the states are available to you. Okay, then it will design the controller to move the poles to these new red colored poles. Okay, whereas observability talks about can we measure all those states or not? Once we measure, we can talk about controllability. Okay, can we measure the states that will be discussed by observability? Okay, you'll understand in a better way once we get to the point. Okay, so now here you can see two things. Okay, so we have this system x dot is equal to ax plus bu. Okay, first consider the top part only. Okay, here, so the that is nothing but our plant. Okay, to understand this pole placement and observer, you need to understand these two images. If you get any doubt, please do ask me. Okay, so now this is our plant. Okay, so from plant, what we are doing, so we are getting this output x. Sorry, we are getting this output x. Okay, let us say, so that is nothing but our output y. Let's say it means that, so we can measure our output. Okay, we can measure our output directly as the state x. Okay, then that state x we are giving as the feedback. We are giving as the feedback. This is the feedback. Okay, so then what we get here, we get fx here. Okay, so we get fx. This fx will be compared with r of t. So we get error. Based upon that error, we generate u of t and substitute here u of t. Then again we get output. This is the sequence. Is this clear? Is this clear? Any doubt?
Clear, sir.
Yeah. So basically, what we do here is, okay, so uh, here we design something called as the pole placement. Basically, pole placement means let us say you have some poles like this. Okay. So let us say you have poles very near to this j omega axis. Still, you can say that the system is stable, but there is a possibility that the poles, since they are very near to the j omega axis, they may shift to the right hand side of the j omega axis. This is left hand side. So this is right hand side. They may shift. Why if they shift, we say that system is unstable. So for that purpose, what we wanted to do is we wanted to place or move those poles, okay, very far from the z omega axis. Let us say these are our new poles, new desired poles. Okay, basically this pole placement technique will do that job. Will do that job. Is this clear? So how it will do that job? It will assume this controller, the input u as some minus kx. What is that minus k? I'll explain later. So assume that it will consider u as minus kx. Okay. Then it will substitute into this equation. Okay. Then it will solve in such a way that the closed loop system will have these new red poles. Is this clear? Is this clear?
Yes, sir.
Okay, the idea. So here to implement this, what this equation needs is, okay, this x must be known. This x must be known. Okay. So here, first basically what we do is, first we will check whether this plant is controllable or not. Once it is controllable, we will design this pole placement to move the poles from these blue poles to the red poles. Okay. That is our basic point. Uh, Here our basic assumption is that this x is known to us, completely known. X means that state vector x, this vector. Okay. So that is our first point. Second thing is, if you see here, the below one, okay. So you are getting x here. Okay. So output is, let us say, when sometimes if that x is not known, if x is not known or partially known, if x is we don't know the x, or if we know it partially. Okay, what is basically x means? Here x is nothing but the state vector x1, x2, etc. xn. Okay, so not known means we don't know any of these x1, x2, etc. xn. Partially known means we will know only x1, x2. We don't know the other values. Okay, in that case, okay, we cannot implement this because this equation requires complete x, but we don't know that. Okay. So what basically this down part will do is, first it will ask this question, whether can we observe or can we estimate or can we find pole vector? Okay. Can we find pole vector? Okay. If yes, then we will design observer for this. Basically what this observer will do is, when this x is not known or partially known, but observability says that we can find, then this observer, okay, start uh, estimating or start observing this x cap, okay, which is nothing but x cap is nothing but x1 cap, x2 cap, etc. xn cap. Is this clear? These are observed values. Is this clear?
Yes, sir.
Yeah. So if you get any doubt, please ask me here, because this small idea we require to understand further things. So basically, what we do is we'll go step by step. Okay. Controllability means, okay, to design this controller. So basically, controllability means, okay, you have these blue poles, okay, but they are very near to the z omega axis. But we are thinking like, since they are very near to the z omega axis, even though they are stable, there is a possibility that they may shift to the right hand side. If they shift, the system becomes unstable. For that purpose, what we wanted to do is we wanted to move those poles so towards left to these red poles. Okay, to do that, we need to apply some input. Okay, u. That input equation is this. Why that equation? I'll explain it later. Okay. If we apply this, okay, then if we find suitable k, okay, that k, if you substitute here, so in place of u minus kx expression, then if you find the overall closed loop transfer function, that will give us these new poles. We'll see in a couple of minutes. Okay, that is our intention. Okay, that we call it is as the pole placement, to place the poles, these blue poles, to the new desired poles. Okay, this is the controller. Okay, to develop that, first we need to check whether can we design that controller. That answer will be given by this controllability check. If we say that system is controllable, then we can, using pole placement technique, we can design this. Is this clear statement? Is this clear?
Yes, sir.
Yeah. Now the below part, basically to design this controller, we need that x. X means this one, complete vector, x1, x2, etc., xn. Okay. But sometimes what happened here is, okay, y is the output. Okay, we are measuring output using some feedback sensors. Okay, sometimes those sensors may or may not give you all these values. Okay, they may not give all the values directly. They may give only some values only, x1, x2 only. In that case, we cannot implement this. To implement that, we need complete x. For that reason, what we do is we are designing this observer. So observer basically it estimates this x cap, which is copy of the x. Okay. To design the observer, first we'll ask the question whether can we observe, can we estimate? Okay. So because we are unable to measure, can we estimate? The answer will be given by the observability. Once observability says yes, observability test, then we can design observer. Clear? So first, so we will check whether my complete X is available for me or not. Okay. If not available, we will go for observer design. Before observer design, we will ask this question. Okay. If yes only, we can design observer. Okay. Then once we have this X cap, or if full X is available, then we will ask, okay, whether it is controllable. If it is controllable, then we'll go for the pole placement. Is this clear? Any doubt? If you can ask me. So the entire week 11 will be based upon this slide only. Okay. So to do this pole placement and observer, okay, checking this controllability and checking this observability are very important. Okay. So we'll come back to this slide once again. Once we start solving the problem, you will understand it. Okay. So now let us go to how to do that controllability and observability. Okay. So first we'll discuss the controllability. Okay. So basically we have this equations, state equation and output equation. Okay. So we say controllability means it's state controllability. What does it mean? Okay. State controllability means, let us say your system is at some initial state at a time t0. At a time t0, the state is x of t0. Okay. At a time tf, okay, the state is x of tf. Now we will ask a question. Is there any existence of u of t? Is there any existence of, what is u of t? Input. Is there any existence of u of t which can take your system from initial state to the final state? Okay. If that kind of u of t is existed, then we say system is controllable. Is this clear? Definition?
Yes, sir.
Okay. So basically this statements gives the same meaning. Okay. You can read this. I'll read it slowly. You'll understand. The state X is said to be controllable at a T naught, because we are starting at T naught. At a T naught, if there exists a piecewise continuous input U of T, okay, which will drive the system to any final state X of TF, in the finite time, Tf minus T0 is greater than or equal to 0, if every state x of T naught is controllable, okay, in the finite time interval, then system is state controllable. Clear? So controllability basically talks about, is there any existence of U of T control input which takes the system from this state to this state? Clear? Clear? Any doubt? Any doubt? Okay. So now, given these equations with A, B, D matrices, how can we check this controllability? Okay. So this is that method. Okay. So once we know that A, B matrices, for controllability, we use A, B matrices only. Okay. For controllability. Okay. For observability, we use A and D matrix. For controllability, A and B. For observability, A and D. Okay. So we will check, okay, system is controllable or not using this controllability matrix. Yes. Okay. So this way we will form the equation. So we call this is as controllability matrix. Controllability matrix. Okay. N is nothing but, so A is n by n. Okay. Order of or size of the A matrix. Okay. So P is nothing but n by P. Okay. So order in the B. Okay. So first what we do, we formulate this matrix S, which we call it is as the controllability matrix. Once we know that matrix, we will find its rank. We'll find its rank. How do we find the rank of a matrix? We find the determinant. We find the determinant. Okay. If determinant is not equal to 0, we say rank is full. Correct? We say rank is full. Am I correct? If it is equal to 0, so rank is rank is full means here rank is not full rank. Is this clear? So once we formulate yes, okay, so we find its determinant, okay, then it is not equal to 0, rank is full. Okay. If it is equal to 0, rank is not full. Okay. So how why rank is full, why it is controllable, this is the out of the scope of this course. We don't require that. Okay. You only remember that given these equations, okay, how to check controllability? Simply using AB matrices, you form this controllability matrix, check its rank. Okay. So if it is not equal to 0, rank is full, it means that rank is n. Okay. If it is not full rank, rank will be less than n. Okay. So if rank is full, we say system is controllable, otherwise not controllable. Is this clear?
Yes, sir.
Or also we can say AB controllable. Okay. So you see this example. Okay. So let us say we have given this x dot is equal to ax plus bu. Okay. So that is something like x1, x2 dot, okay, equal to, these are the AB matrices. So minus 2, 1, 0, minus 1. So x1, x2 plus b is the 1, 0, input is u. So it is given like that. Okay. So this is your A matrix, B matrix. Is this clear? Okay. Now the controllability matrix is yes in this way. Now here n is equal to 2. Why n is equal to 2? Because A is order is 2 by 2. Okay. Now substitute into here. So 2 minus 1 is 1. So it means that these are the two terms. That means your S is up to first two terms only. Am I correct? Okay. So in S, what is our first column? The first column is B. Okay. What is the second column? The AB part. That is this part. Is this clear? Any doubt? Any
Yes, sir.
doubt? Yeah. So now you have S matrix. If you find the dead, what is the dead? the det is 0. Okay. Since det is 0, so what is its rank? The rank is not equal to 2. Okay. The rank is 1 only. Since rank is not n, okay, or not 2, so system is not controllable or uncontrollable. Is this clear?
Yes, sir.
Yeah. So that is how you will check. Okay. Here n is equal to 2, we got only 2 terms. If n is equal to 3, we will get 3 terms. Clear? Any doubt? This is how we will check. Okay. So let us see this example also. Okay. So is there any other way of doing this? Okay. So we can do that. Is there any doubt here?
No, sir.
Yeah. If you have any doubt, you can ask me. So basically here we are talking about controllable, not controllable. What is the meaning of this? Can we check the same thing using other way? Other way in the sense, not by using the AB matrix, this S matrix. Instead, we can also do the same thing by using the similarity transformation. Okay. Similarity transformation, what basically we do is, so we have this x dot is equal to AX plus BU. Okay. So we do this similarity transformation by choosing so the transformation y is equal to px. Okay. Where P is some matrix. Okay. Where P is some matrix. You take y dot is equal to P x dot and substitute this x dot from here. Okay. So x dot is equal to P inverse y dot. P inverse y dot. So you substitute x dot is equal to, so expression from here. Okay, this expression. So finally you write y dot is equal to AY plus BYU. Okay, where AY is nothing but this expression, BY is PB. Okay, so by doing transformation, what we are doing, so basically this is our original system. Okay, this is transformed. Okay, this is the transformation. Yes, y is equal to px. Okay, now if you see this original system, okay, let us say P is some matrix. Find this AY and BY. Okay, so P is some matrix where P inverse is existed because we need to take the inverse here in this term. Okay, so P, PA, P inverse, okay, then PB. Okay, so this is the equation. Okay, so this equation y dot is equal to AY plus BYU. So this equation. Okay, so now if you see this equation, okay, what do you understand here? So what do you understand? Okay, so if you see this equation, basically in the first row will give you this equation. Am I correct? Minus 2y1 plus u of t, correct?
Yes, sir.
Second row will give us only minus y2. Okay, so here input is 0. Okay, basically what you understand here, the y1 has input term, correct? Y2 has no input term. Am I correct?
Yes, sir.
So that is the meaning of uncontrollable. Okay, if it is controllable, both y1, y2 will have the input term. Okay, here u of t affect only y1, not y2. So the system is uncontrollable. That is the basic meaning. Is it clear?
Yes, sir.
So, but that controllability, uncontrollability, we will check directly by using this S matrix and its rank. Clear?
Yes, sir.
If it is controllable, here also we will get that u of t term. Okay, but in this case, it's not controllable. Okay, yeah. So any doubt? Any doubt?
Sir, which method should we use? Like both the methods are easy.
No. This one only.
First one.
So this one only, S matrix only.
Okay, okay.
Okay, so that is straightforward. Okay, clear. So next directly I will go to, this is how you will check the controllability. Okay, next observability. Okay, so here also same thing. Okay, system is observable or completely observable if every state variable, okay, if every state variable of the system affects some of the outputs. Okay, every state variable of the system affects some of the outputs. Basically, what is that meaning? Okay, so it says that, sorry, it says that you have these two equations. Okay, we can say the initial state x of t naught. Okay, initial state is said to be observable. Okay, basically observable means can we estimate it, because that is not directly available at the output. Okay, so output measurements are there. So using those, can we find this x of t naught? That is the basic question. Okay, so the question is x of t naught is said to be observable. The question we need to ask is whether x of t naught is observable or not. It is estimatable or not. Okay, so here this observability test will answer that question. Okay, it is observable if given any input u of t. Okay, so for any input u of t, there exists a time tf greater than t naught. Okay, the knowledge of u of t, okay, knowledge of the matrices a b d e, okay, knowledge of the output, okay, they are sufficient to determine x of t naught. Okay, here to find this, what you need, so the knowledge of, okay, so u of t, knowledge of u of t, okay, so the matrices and the output c of t. So these are enough to find this x of t naught. Okay, then we can say that the x of t naught is said to be observable. Is this clear? Is this clear? So if every state is observable, then we can say that system is completely observable. Clear? Is this clear? Any doubt? So basically here you are very much interested to find what is my initial state, because here your x is nothing but, so x1, x2, etc., xn. Okay, you wanted to find what is x of t naught at initial time. What are these values? x1 of t naught, x2 of t naught, etc., xn of t naught. That is your question. Can I find my initial state? Okay, can I find my initial state? That is your question. So the observability says that if system is observable, knowledge of these things are enough to find your initial state if system is observable. Is this clear statement?
Yes, sir.
Yeah. So similarly, again, just like the previous case, here we use the A matrix and D matrix to find whether the system is observable or not. Okay. So what we do here is we will call something called as the observability matrix. Okay. So this is that matrix: D transpose, A transpose, D transpose, etc. So A transpose power n minus 1, D transpose. Okay. Again, here what we do, we substitute those D and A matrices. Okay. Again, we will find the depth of V. Okay. And check whether it is not equal to 0 or equal to 0. If it is equal to 0, then rank is n. If it is not equal to 0, rank is n. If it is equal to 0, rank will be less than n. Clear? So what we require for the system to be observable, we require full rank. Then we say that AD is observable or system is completely observable. Clear? So again, this is the example. I can give one example. You will understand much better. Okay. So one example I'll give you. Yeah. So let me tell you an example. So let's say we have this. Uh, so x dot is equal to -6 -5 1 0. Okay, x plus 1 0 u. Okay. So y is equal to 3 1 x. Okay. So we need to check whether it is controllable and observable or not. Okay. So what is controllability matrix? Controllability matrix is B, AB, okay, A square B, etc. A power n minus 1 B. Am I correct?
Yes, sir.
So here this is 2 by 2. That means n is equal to 2. So 2 minus 1 is what? 1. Okay. So what is the controllability matrix then? For this case, B and AB. Correct?
Yes, sir.
So the B will be 1 and 0. Once you find AB, okay, so you will get, I'm giving that value directly. AB multiplication is -6 and 1. Okay, so you are finding the det. Okay, so det of C will be 1 minus 0. Okay, that is 1, which is not equal to 0. Hence, system is what? So the rank is what? Rank is 2. Correct? Hence, system is controllable. Am I correct?
Yes, sir.
Yeah. So similarly for the observability, okay, here this we are saying this is C matrix. Okay. So the observability, what we do? Observability matrix. That is nothing but C transpose. Okay. So A transpose, C transpose, okay, etc. A transpose whole power n minus 1 C transpose. Okay. Here also n is equal to 2. Okay. So that means n minus 1 is nothing but what? 2 minus 1. That is 1. That means what? In this case, observability matrix is C transpose, A transpose, C transpose. Am I correct? Okay. So again, if you do that calculation, C transpose, this is your C matrix. Okay. So what is C transpose? So 3 comma 1. Am I correct?
Yes, sir.
And again, if you find this A transpose, C transpose product, you will get this one. Okay. So what is det? Det of this O matrix is, so 3 multiplied -15. Okay. So minus of -17 multiplied 1. Okay. So which is nothing but -28, which is not equal to 0. Correct. So which is nothing but rank is 2. Okay. Hence the system is observable. Clear? So controllable and observable. Is this clear? So how to check controllability and observability? Any queries here? Any queries? Any queries? So hope you can do this problem easily. Okay. Next. So once we understand how to check this controllability and observability, now the next step is pole placement design. Okay. So let's go to that. First understand that what is that pole placement design. So I'll explain this one again. Okay. So the first top part. Okay. I'll explain it again so that you'll understand much better. Okay. So we have these poles, okay, which are near to this j omega axis. You they are stable poles because they are on the LHS side. Okay, but they are near this j omega axis. You might feel that they may shift so to the right side. That's why you wanted to move them so to more to the left side. Say here. Is this clear? Is this clear? Any doubt? That is our first aim. to move the poles from these blue poles to the red poles. Okay. Then uh, the pole placement basically will do that job for us. Okay. So by properly designing this U in this form, U is equal to minus kx. Okay. So what we are doing is this U is nothing but the control input. By substituting minus kx here, we are controlling the entire plant, go from these old poles to the new poles. Okay, we are saying that. So take your system from one state to the other state. To do that, first we need to check the controllability. Clear? So we know how to check the controllability. Is this clear? After checking the controllability, we come to this step. So pole placement method. Okay, we can place or we can move our blue poles to any poles, any our desired poles, the red poles. The pole placement will do that job for us. Is this clear?
Yes, sir.
Yeah. Now we will see what is that pole placement technique is. Okay, so if you don't understand anything, you can ask me clear. Okay, so I'll use the same slides. Okay, so basically, uh, we already know that location of poles will talk about stability. Okay, if poles are existing in the left hand side, okay, system is stable. Okay, if any pole is on the right hand side, we say system is unstable. Okay, so the location of poles, okay, so they'll talk many things. Okay, so they'll talk about the transient response. They also talks about the settling time, overshoots. Okay, so location of poles also decides the whether the disturbance is more or not. So location of poles is very important for any system. Okay, so now the question we ask is, can we design an appropriate control law? That is nothing but that U. Okay, U, can we design this, okay, in such a way that it can place our poles to any desired locations. Wherever we are interested, can we place our poles there? Okay, so it means, it basically means these are the existing poles. Desired poles means any new poles, let's say somewhere here. Okay, can we design any control law which takes our system from this poles to this poles? Okay, the pole placement technique will do that job for us. Okay, so the first step before going to the pole placement is we need to check for given x dot is equal to, so ax plus bu. Okay, we need to check the controllability test. Okay, how do we do that? We form this C matrix, controllability matrix. Then we check the rank by finding its determinant. If rank is full, we say that system is controllable. That is also called as the another language, Kalman rank condition. So this is the Kalman who found this entire methodology of controllability and observability. So that's why we call that is as Kalman rank condition. Is this clear? Is this clear? So first, before designing pole placement, we must check whether the system is controllable or not. Okay, this is the step. So once we decide that, okay, system is controllable. So these are other assumptions. System is controllable. Okay, it means that all the state variables are measurable. Okay, so then we go for the pole placement. Okay, so I'll tell you. So basically, what is this pole placement is? First, we choose. We have this x dot is equal to ax plus bu. If you are getting any doubt, you can ask me directly. We have this ax plus bu. We choose this control input u as minus kx. Okay. Then substitute in place of u. What do we get? So we get ax plus b minus kx. Am I correct?
Yes, sir.
So that is nothing but a minus bkx. Am I correct? That a minus bk we call, because basically this is a open loop. After substituting minus kx here, it will become a closed loop. So we call this matrix as ACL, closed loop A matrix. So that is this one. Clear? So ACL is nothing but A minus BK. Okay. So once we substitute, U is equal to minus KX. Okay. Now, okay. So if this is given to us, X dot is equal to AX plus BU. Okay. If you take this SI minus A, that equal to 0. Okay. We will get one polynomial. Okay. We'll get one polynomial as S power N plus alpha coefficient S power N minus 1. So, etc. At last, we have alpha is equal to 0. Okay. So, that is our polynomial given A matrix. If we find this. Okay. Here, our objective is to find this K, which we also called as the gain matrix. Okay. We need to find this gain K in such a way that, okay, okay, so this closed loop system, this part, if you take the determinant, okay, and these are the roots. Okay, these are our desired poles. Closed loop system, once we substitute that K, okay, the closed loop system we will get the roots as mu1, mu2, mu_n. They are nothing but the desired poles. Is this idea clear?
Yes, sir.
Is the idea clear? If you have any doubts, you can ask me. The idea is very simple. Okay. First, X dot is equal to AX plus BU is given to us. That is a open loop system. Okay. In that, we are asking a question. Can we design a control law? Okay. So basically, we have X dot is equal to AX plus BU. Okay. So which has false location, the red color. Okay. But we wanted to place our poles to this blue color. Can we design a control law for that? That control law is nothing but this one. U is equal to minus Kx. Here our job is to find that K. What is that K? Okay. So it means that you have a system, you have a plant. The plant already has the poles. Okay. You're not satisfied with the poles. Now what you are asking is, can I design a control law? So that poles, let's say P1, P2, old, you wanted to place them to the new poles, P1 new, P2 new. Okay. What is that K value we need? Is it clear? What is that K value we require? So if you see one example, you will understand it. So this is the process what we do. So first we check the controllability using our regular method. Then you define this K. Once you define this K, so this is our closed loop system characteristic equation. Equate that one to the new poles polynomial. So you have left hand side, you have right hand side. Left hand side you will get one polynomial. Right hand side you will get one polynomial. So compare the powers. And get the values of K1, K2, K3, etc. Clear? So let us see the example. So the example is, let me start it freshly, so we'll understand it a better way. Okay, so the example. So if you get any doubt, you please ask me. Okay, so you have a system X dot is equal to AX plus BU. Is it clear? So you should understand from this example what is this pole placement technique is. Okay, you have this system X dot is equal to AX plus BU. So from the A matrix, you can find the characteristic equation, which is nothing but, so SI minus A equal to 0. Is it clear?
Yes, sir.
Once you know A matrix, you can find characteristic equation. That is nothing but this one. Here A matrix is not given to you. Directly characteristic equation is given. Okay. Now, so if you find the roots for this equation, okay, the roots are -1, -2, -3 for this equation. Roots. Okay, that means they are your poles. Okay, they are your poles. You can see here the blue colored ones. Correct? -1, -2, -3. Is this clear? Any doubt? Okay, -1, -2, -3. Okay, now what you wanted to do is you're not satisfied with these poles. Okay, but what we wanted to do is you want your poles to move this location. -1 you don't want to change, -2 you don't want to change, but -3 you wanted to move to -2. Is this clear? Okay, these are your given poles, but you want those poles to move to here. So that means these red colored poles. Only the change you are expecting is -3 to move to -2. The other two poles has to be same. Clear? Is this clear?
Yes, sir.
So now we are designing this controller minus kx. Okay, k is nothing but k1, k2, k3. Why? Because your order is 3. Okay, so k1, k2, k3. So here you can see, so just now we saw for closed loop system, this is nothing but ACL, right? ACL. So you are finding the determinant of SI minus ACL, closed loop system. Am I correct? Okay. So it means that once you design proper K, okay, so this is your characteristic equation that has to be equivalent. So this is your characteristic equation. This is the expression you are getting. That has to be equivalent to the, what? The polynomial comes from the new poles. That is this one. What are the new poles? -1, -2, -2. Okay. So that will be characteristic polynomial is s plus 1, s plus 2, s plus 2. This is the polynomial. Now you compare these two, same powers. What are the powers? So s cube powers are 1. We don't to take. Okay. S square powers are here 6 plus 1, k1, here 5. Okay. This one. So s powers are 11 plus k2, here 8. This is this. Constant is 6 plus k3 and 4. This is this. Clear? Now you get these three values, k1, k2, k3. Is this clear? Is this clear?
Yes, sir.
So this is the expression. This k, if you substitute here, okay, can you tell me how this polynomial will change? This k, if you substitute here in place of k1, k2, k3, what that polynomial will be? What that polynomial will be? Hmm? What is k1? K1, K2, K3. Just substitute it. So K1 is -1. Okay. K2 is what? -3. K3 is what? -2. Now tell me what is that polynomial?
Sir,
What
it
is
is
that polynomial?
low s cube plus 5s square plus 8.
Yes. S cube plus 5s square plus 8s plus 4. So exactly the desired polynomial. The characteristic equation of the desired poles. Correct?
Yes, sir.
Now you understand the pole placement technique. Here our job is to find the K which place the poles to the desired pole location. Okay, so we simply find this by using the comparison. Okay, any doubt here? Any doubt? So here our main job is to find that k. Okay, so based upon that we have three methods. Okay, so the first method is this one, very basic method. Okay, second method is based upon the canonical controllable canonical form. Okay, basically controllable canonical form means, okay, so you can see this differential equation in the down. Can you see this differential equation?
Yes,
Okay,
sir.
so what is this differential equation? Has a n minus 1 d n minus 1 y by dt n minus 1 a n minus 2 d n minus 2 y by dt n minus 2. So you have a system. So that system, if you write down the modeling equations, it turns out to be like this. It turns out to be like this. This equation, okay, you wanted to convert to x dot is equal to ax plus bu. That means you wanted to find what is A matrix, what is B matrix. Okay. This controllable canonical form, just by looking at these coefficients, you can write your AB matrices. Okay. These are your AB matrices. So you can check it clearly where you are placing those coefficients. Okay. So you are placing the coefficients at this location. Am I correct? So this is called as the controllable canonical form. Is it clear? Is it clear? So you have a mechanical system is given to you. Okay. So once you write your kinematic equations, okay, so you are getting a differential equation like this. Once you have this differential equation, okay, so you wanted to convert this differential equation into x dot is equal to ax plus bu. Okay, so x dot is equal to ax plus bu. So directly we can write these AB matrices by placing all these coefficients at this location. Okay, so that means A and B matrices are this form. This is called as the controllable canonical form. Just by looking at the coefficients, we can find AB matrices. Now, this method 2 says if the given system is in CCF form, okay, controllable canonical form, it means that A and B matrices are this form. All the others are zeros and ones except the last rows. If that is the case, so the method 2, how do we find that matrix? How do we find that gain k with the same expression, same controller? That is this method 2. Here what we do, so this is our closed loop A minus bk. Okay, so substitute everything. So A, B and k. So the last row will modify in this way if you write it. Okay, so that is first thing. Next, our desired poles are mu1, mu2, mu_n. So what do we do? What do we do? So we will take the same way. So we'll take same expression. What is that expression? Det of Si minus A minus Bk, which is equivalent to S minus mu1, S minus mu2, etc. S minus mu_n. So same expression what we saw previously here. Okay. If you put it like this, so this right hand side, this is the polynomial. Okay. The left hand side, okay. So if you find the left hand side, this ACL, okay, then compare the coefficients. You will get your K1, K2, etc. Kn. Is the method clear? Method clear? So if you just write it, you will understand this. So this is an example. Okay. So same thing. So you have this x dot is equal to ax plus bu. So AB matrices are not given, assuming that A and B are in that CCF form. Okay, once you take this characteristic equation, Si minus A det, so we are getting this characteristic polynomial. Okay, so once we have that characteristic polynomial, okay, so since the A and B matrices are in CCF form, we can get this A2, A1, A0, which are directly from the polynomial. Okay, so these are the polynomials. Okay, now we wanted to place these poles, the new locations, -1, -2, -3. Okay, so then what we do from here, we can write s plus 1, s plus 2, and s plus 3. This is our desired characteristic polynomial, this one. So that is this. Okay, now compare with alpha 2, alpha 1, alpha 0 from here. And you'll get the values of K1, K2, K3. Okay, so once you get K1, K2, K3, what does it mean? So the K1, K2, K3 is like this. Okay, K1, K2, K3 is the row vector. X is column vector. You multiply both. Here in this problem, we got K1, K2, K3 as 2, 3, 1. 2, 3, 1. Okay. Then you multiply them, you get -2x1, -3x2, -x3. So substitute this u in the basic equation. Okay. So this ACL, if you find the eigenvalues, again you'll get the same values, -1, -2, -3, which are nothing but what? Which are nothing but the desired poles location. Desired poles location. Is this clear? So if you just solve this example, you'll understand it. Okay, this is method 2. Okay, so then you have method 3. Okay, so which is nothing but which is also called as the Ackermann formula. So basically this is based on the Cayley-Hamilton theorem. Okay, basically Cayley-Hamilton theorem says this one. So you have this characteristic equation, lambda I minus A. Let's say if you expand that, you will get this polynomial. Okay, if you expand it, you'll get this polynomial in terms of lambda. And A0, A1, etc. They are all coefficients. Okay. Now Cayley-Hamiltonian theorem says that you just replace that lambda with A matrix. Okay, that also will be equal to 0. Is this clear? Is this clear? First, what we do, so Cayley-Hamilton theorem. So you have characteristic equation. When you are trying to finding the eigenvalues, you take lambda I minus A. Okay, you take the det equal to 0. You get this polynomial A0 plus A1 delta plus A2 delta square, etc. An delta power n equal to 0. Okay, replace that lambda with A matrix and again do all the calculations, you'll get 0 only. It means that Cayley-Hamilton theorem says that every matrix A satisfies its own characteristic equation. This one. Every matrix A satisfies its own characteristic equation. That is the main point. Okay. Any doubt here on the Cayley-Hamilton theorem? You can ask the doubts. Okay. So now we call this polynomial as pi of lambda. Okay. When we substitute lambda, when we substitute A, that will be pi of A tilde. Okay. So it satisfies its own characteristic equation. Okay. That is Cayley-Hamilton theorem. So in the method 3, basically what we are looking is the same equation holds good. Si minus a minus bk, that is one side. We are interested to find what is this k, and desired poles polynomial on the other side. Okay, so we keep this desired poles polynomial as it is, and right left side, okay, we will modify this with polynomial of pi of lambda. Okay, so that's what the all this derivation says. Okay, then finally we compare. Okay, we compare, we will get this k matrix. So in the derivation, we will use that Cayley-Hamilton theorem polynomial, this one. Then we find the K matrix. So what this K matrix is? So the first one, then controllability matrix, then the characteristic polynomial. Okay, if we see that derivation, we'll get that. This is the third method. Okay, you can use any method when the question is on pole placement technique. Okay, so the first one is simpler. The second one is when uh, the uh, the state space equations are in CCF form. The third one is based on the Cayley-Hamiltonian theorem. Okay, you can use any method. So this is that example. So we have A matrix, B matrix. Okay, so this is your control law. So the desired poles are -2 plus J4, -2 minus J4, S is equal to -10. Okay, use the same thing, find the controllability matrix. Okay, so this is the overall method. So this is method one. Okay, so method one simply says that you take the k and equate it, take the k polynomial, equate it to the desired polynomial, compare the coefficients, you get this. Okay, so then the method two, if they are in CCF form, here A and B matrices are in the CCF form. Okay, if they are in the CCF form, okay, compare the coefficients. So same thing. The third one is method three. Okay, you will use the Cayley-Hamiltonian theorem polynomial, characteristic polynomial, okay, to find the k. Okay, so I hope the idea of the pole placement technique is clear. So if you still have any doubts, you can ask me on the pole placement technique. So just solve only the existing problems in the video. That would be enough. Okay. So are there any questions? Are there any questions?
Sir, method 2 and 3 are very lengthy.
No, no, no. You should write them once. You'll understand it. That's why. Uh, when you are applying, you can apply any method. Okay.
Yes, sir.
Yeah, yeah. And in MATLAB also you have this command for method 3. So this if you know your A and B matrices and the desired pole vector Z, okay. So directly you can use this control system toolbox and ask for actor A, B, Z. It will directly give us what? It will give us the K. Okay, so you can use this code and to test this. Okay. So in next live, I'll be explaining this observability and observer design. Okay, so that time you please go through this slides of pole placement, and if you get any doubts, you can ask me. Because pole placement technique is one of the important technique. Okay, and we'll take simple the one the surprise test, finding this controllability and observability. Okay, yeah. So I'm giving so surprise test. So A matrix is like this. So I'm giving 3 by 3. Minus 11, minus 6, 1, 0, 0, 0, 1, 0. So B is equal to 1, 0, 0. Okay. C is equal to 0, 1, 3. Okay. So check both to controllability and observability. Okay, so solve it, take the picture and send me an email. Right now the time is 6:50. So you can send me by 7:15. So you have some 25 minutes time. Okay. So we'll stop here and continue in the next slide with observer design. Okay. Thank you.
Sir, can you tell your mail ID once?
My email ID, Chakravarti underscore Z.
Okay, sir.
Yeah, yeah. So it's here already, I think. So Chakravarti underscore J at study.iitm.ac.in. CHAKRAVRTHIJ. So let me post it there. Just a minute. So copy. I'll post it in the chat box. Yeah. Okay. Thank you. We are closing this call.